At Ingevity Pavement Technologies, everything we do is interface science. For us, it's all about what's going on at the interface, or rather the boundary between two substances. The interactions that are occurring at a molecular level when two media, solid, liquid, or gas, meet. Our mission is to use chemistry to affect what happens at those boundaries. And amazingly, when we do, water is cleaner, dyes disperse better, asphalts mix and compact more efficiently, and we do all this with renewable resources. Of course, the big question is how? Well, we actually create special molecules that enable a sort of chemical harmony at the interface. But to explain how those special molecules work, we'll need to go back and review Chemistry 101. You probably all remember that big chart that hung on the wall of the high school science lab. It's the periodic table, a cheat sheet of sorts, that categorizes all the unique atoms or elements that make up matter: hydrogen, sodium, carbon, nitrogen, oxygen. Now you will recall that when atoms combine, they form molecules. For instance, when an oxygen atom bonds with two hydrogen atoms, it creates the molecule H2O, or water. You'll notice the structure of the molecule. The oxygen atom has an excess of electrons and is negatively charged. The hydrogen atoms have fewer electrons, and they are positively charged. The molecule has poles, much like those on our planet. And these poles make the molecule polar. Molecules with a more equal distribution of electrons simply cancel each other out and are nonpolar. And this is important because polarity affects solubility, the ability of two substances to mix. So if we mix polar H2O molecules with other polar molecules, let's use ethanol, the two substances mix. The alcohol is soluble in water, and nature likes this combination. You see, polar molecules like to be with other polar molecules. But if we go back to our periodic table and we make a nonpolar molecule, like cooking oil, and then we mix our oil molecules with our water molecules, and I'm sure you know where this is going. Oil and water don't mix. Nature doesn't like this combination. Nonpolar molecules only like to mix with other nonpolar molecules. They may temporarily disperse, but the oil molecules stick together and the water molecules stick together. And given a little time, all of the like molecules will find each other. But what if there was a molecule that had both polar and nonpolar characteristics? A molecule that could bridge the great divide between the two. Surfactant chemistry, coming up next. So polar and nonpolar don't naturally mix, but we can persuade them. In the case of asphalt paving, it takes a tremendous amount of heat energy to persuade the asphalt, a nonpolar oil, to coat the rocks, made up primarily of polar molecules, like quartz. However, at Ingevity Pavement Technologies, we've discovered a way to replace much of that heat energy with chemical peacemakers. Molecules that can bring together substances that would otherwise be, well, polar opposites. They're called surface active agents, or surfactants. Molecules derived from fats that have both polar and nonpolar qualities. The classic surfactant molecule. It has a polar head and a long carbon chain for a tail. For the sake of demonstration, we'll use a bit of shorthand and transform our surfactant molecule into what we call a lollipop. If we could see what was happening at a molecular level, magnifying the molecules over 1 trillion times, and we added our lollipops, our surfactant molecules, to a beaker full of H2O, the surfactant molecules immediately go to the interface, and the polar heads, doing what nature likes, are drawn to the polar water molecules. But when the surface is saturated, when no more surfactant molecules will fit, something really interesting happens. In a sort of dance, the excess molecules find each other. The nonpolar tails all want to be together, and the polar heads all want to be together. And they form spheres called micelles. Now I'm sure you're thinking, that's all well and good, but how does it help me? For that explanation, we'll turn to the most well-known surfactant on the planet, soap. That's right, soap is a molecule derived from fats that has, ta-da, a polar head and a nonpolar tail. So, if instead of a beaker of water, we have a glass that contains not only water, but also remnants of cooking oil, and we add our soap, or surfactant molecules, they do the same thing that they did before. But this time, the nonpolar tails of our soap molecules and the nonpolar oil molecules are drawn together. The oil is captured within the micelles and can now be easily rinsed away. But where do these miracle molecules come from? And how do we use them to help make our planet and your lives better? Evotherm Chemistry 101, coming up next. Surfactants are surface active agents, incredibly useful molecules that can markedly change how substances, especially substances that aren't naturally compatible, interact with one another. But where do these molecules come from? It's not like they grow on trees, or do they? For us, the process starts with sustainable forestry, which means for every tree we harvest, we plant 5. Our tree, 70% is made up of fiber used to make paper products. 28% is a substance called lignin, a dispersant used in a variety of applications. And that remaining 2%? Natural tree oils. We recover these oils and derivatize them, change them. We literally manipulate their structure through chemical reactions to create a desired effect. And in this case, the desired effect is the creation of a molecule that will allow our scientists to use what nature likes to improve the process of asphalt paving. But how does it work? Let's go back to our beaker. And this time, instead of filling it with water, let's fill it with oil. Like before, we'll add surfactant molecules. And remember, this is what's going on at a molecular level. The nonpolar tails are attracted to the nonpolar oil, and the molecules begin to form micelles. Since the surfactant molecules are in oil instead of water, the micelles are inverted. All the polar heads want to be together, and all the nonpolar tails prefer the oil. If water is added, it is drawn to the polar heads and resides happily inside the micelles. Now what if we applied these same principles to the production of asphalt? Traditionally, it has taken the application of extreme heat to get the nonpolar asphalt and oil to coat the polar aggregate, rocks made up primarily of polar minerals like quartz. But when Evotherm is introduced, a solution that includes our specially engineered surfactant molecules, much of the heat energy is replaced with chemical energy. The Evotherm molecules go to the interface. The polar heads are attracted to the polar properties in the rocks, and the nonpolar tails attract the oil. Any water that is present, whether added or naturally occurring in the aggregate, is captured within the micelles. Our aggregate, our rocks, are now coated in asphalt oil, and nature did most of the work. But superior coating alone isn't enough to build a road. We'll need those micelles that remain in the mix. Evotherm Chemistry 201, compaction, coming up next. Warm mix asphalt. The science behind Ingevity's Evotherm allows us to replace heat energy with chemical energy. The result? A superior mix produced at much lower temperatures. But that's only part of the story. The key to a long-lasting weather-resistant road is compaction. And you guessed it, the same surfactant molecules that improved mixing and coating are improving the compaction process as well. To understand how, we'll need to know more about viscosity. Viscosity is a measure of a fluid's resistance to flow. Water is thin and has little to no resistance. Honey is thicker and has some resistance. And a typical asphalt oil? Very, very thick. It becomes obvious at this point why asphalt has to be heated to have any hope of coating the rocks, and why the mix must be kept hot to be compacted. When you heat asphalt, it becomes less viscous. In fact, if you heat it enough, asphalt will become as thin as water. But as it cools, it thickens. And that is why hot mix asphalt paving is such a time-sensitive endeavor. If the asphalt cools too much, it will be too thick to compact. However, if Evotherm is in the mix, a road can be compacted at lower temperatures, temperatures that would render traditional hot mix asphalt useless. Our special chemistries allow us to build a roadway with asphalt that is 10 times more viscous than hot mix. Here's how. During the coating process, all of the excess surfactant molecules formed micelles within the mix. These micelles have very low viscosity and offer no resistance to the shear stress created by the rollers. They also have dynamic properties that allow them to deform, change shape, and still stay intact. So when the asphalt is compacted by a roller, the micelles act as slip planes. They let the rocks and asphalt slip past each other and compact into a very solid surface at temperatures over 50 degrees Celsius, that's 100 degrees Fahrenheit, less than hot mix. And these lower temperatures translate into tremendous fuel savings, a better work environment, and dramatic reductions in emissions. A clear example of the power of interface science, Evotherm, improving our roadways and our environment. And it's all thanks to the innovative technologies developed by Ingevity.